structures. Yeah, in this talk, I would like to understand this why there is this kind of complicated structure, and I'd like to introduce the topological property of this complicated structure of the non-Hermitian band. For example, if we think about the gamma space, this is Hermitian degenerate points like this. This is drag points. If we remove these Hermitian degenerate points, these two bands are separable. It's very simple. But in this case, if we enlarge this part, they make this kind of branch cut structure. There is branch point. This point is non-Hermitian degenerate points. Real parts and imaginary parts of energy are the same at this point. However, there is another branch cut structure here. In that case, the real parts are the same, but imaginary parts are different. So this branch cut structure is not degeneracy. So if we remove these degenerate points, these two bands are not separable. So it's totally different from the Hermitian degenerate case. So this kind of complicated band structure, we have to understand why this kind of band structures occur in non-Hermitian system. I'll talk about that today. Okay, I'll start from very simple linear equation. This is X is n column vector. This is n by matrix. This is a linear equation, and we can know the time evolution using this equation. And this equation can be used in many various physical situations. In quantum mechanics, this is a Schrödinger equation for n-level system. In conventional and Hermitian quantum mechanics, this is a Hermitian matrix. And this equation can describe the classical mechanics, that is a Newton equation for n-coupled oscillators. And electric circuit, this can describe the Kirchhoff law for linear elements. And linear wave system, this is the evolution of the n modes. And in open quantum system, this equation is Lindblad equation for n element dense matrix. There are so many physical situations, physical systems, which can be described by this linear equation. In this equation, this D is important information. This is matrix, but except the Hermitian quantum mechanics case, in generally, this matrix is non-Hermitian for the other systems. And nowadays, we think about the many non-Hermitian quantum mechanics study. In the case, this D is a non-Hermitian matrix. In Newton equation and Kirchhoff law and evolution and Lindblad equation, this is a non-Hermitian matrix. So if we know the eigenvalue and eigenstate, eigenvector of this non-Hermitian matrix, we can understand this linear equation. I mean dynamics of this system. Of course, in conventional quantum mechanics, this is Hermitian. So in this talk, I would like to understand the eigenvalue, eigenstates of this non-Hermitian matrix. If we think about the non-Hermitian matrix can have complex eigenvalue. It's different from Hermitian matrix. Of course, non-Hermitian matrix can have real eigenvalue or complex eigenvalue. And non-Hermitian matrix can have non-orthogonal eigenvectors. It means the angle between two eigenvectors can be less than 90 degrees. If we decrease the angle, at some time, it's possible that the two eigenvectors are the same because the non-orthogonal eigenvectors. So that is non-Hermitian degeneracy. So this is degeneracy, but it's totally different from Hermitian degeneracy. In Hermitian degeneracy case, eigenvalue are the same, eigenvector are different. But non-Hermitian degeneracy case, eigenvalue are the same, eigenvector are also same. The name is degeneracy, but their Hermitian degeneracy and non-Hermitian degeneracy are totally different. And this is called the exceptional point. I'll explain about this later, more details. And because of this kind of properties, the eigenvalue spectrum in non-Hermitian matrix has non-trivial topological structures. So today I talked about this eigenvalue spectrum and their non-trivial topological structure. Okay, if we think about the time evolution of non-Hermitian matrix, this time evolution is non-unitary, and they can make a kind of attractors. It means in Hermitian system, in general case, they have the extended modes. It's not easy to achieve the localization in general case, but in non-Hermitian matrix, the localization is very well achieved in very simple situation. And sometimes they can have they can make the collective phenomena like the synchronization. And this can make some kind of clustering of the states. And of course, sometimes this requires the nonlinearity. And other properties, near the exceptional points, this variable changes dramatically for small perturbation. And this property comes from non-Hermitian matrix. So today I focused on the non-Hermitian matrix or non-Hermitian effective Hamiltonian at this part. Using this interesting property, there are many applications for sensing and lasing, grading networks in various systems: microwave, optical, acoustic, electrical, mechanical, quantum systems. Yeah, I don't talk about the many details in the different system. My main focus is the topological property of the non-Hermitian system in the simple tight binding model. And if we understand the topological property of the non-Hermitian bands, we can apply our theory to the many different systems in experimental or other theoretical work. Okay, I'll start to explain the closed system versus open system. If you have the system, this is a closed system. In this case, there is no interaction between the system and environment. And if you think about the open system, there is environment, there is interaction between system and environment. However, if we think of the whole universe, like the conventional quantum mechanics, we can describe these two different systems using the Hermitian Hamiltonian. In this case, this Hamiltonian is system Hamiltonian, and environment Hamiltonian, and the coupling Hamiltonian. This is also Hermitian. But sometimes this Hermitian Hamiltonian to describe the whole universe is very complicated or it cannot be realized. So sometimes we use the non-Hermitian effective Hamiltonian for only describe this part. In that case, the environment traces out to the effective Hamiltonian. If we think about the non-Hermitian effective Hamiltonian, there are two typical ways to make the non-Hermitian effective Hamiltonian. First is if we use the complex potential. It means that this is matrix. For example, this is a matrix Hamiltonian. On-site potential is real in Hermitian case, but if we use the complex potential I mean the complex on-site value, that in that case the Hamiltonian can be non-Hermitian. Usually it means the energy, our potential energy gain or energy loss is possible. Because non-Hermitian Hamiltonian is not energy conserved system. This is one way. And another way is that we can control the boundary condition. For example, in conventional Hermitian Hamiltonian, there is incoming and outgoing boundary condition together. But in non-Hermitian Hamiltonian, if we use only outgoing boundary condition, in that case, we can construct non-Hermitian Hamiltonian because this boundary condition is included in the Hamiltonian. For example, if we have the cavity like this, if this is one cavity, there is the resonance mode here, and there is decay in this direction, but there is no incoming wave. We can obtain the resonance mode, and this resonance mode have the lifetime, and their eigenvalue can be complex using this outgoing boundary condition. So yeah, we can make the non-Hermitian Hamiltonian in other ways, but these two ways, the very typical ways. Using this non-Hermitian effective Hamiltonian, we can describe many different physical systems: photonics, mechanics, open quantum system, and mesoscopic system. In that case, the physical origin of non-hermiticity are different depending on the system. In photonics case, gain and loss of photons. Sometimes this is realized by the dielectric interface, or sometimes this is realized by the absorption of the material or lasing amplification. And in mechanics, friction can make the system non-Hermitian. And open quantum system, dissipation can make the system non-Hermitian. Using this kind of the non-Hermitian effective Hamiltonian, we can make our equation is non-Hermitian. Okay, yeah, this is summarized non-Hermitian physics study, recent non-Hermitian physics study. Yeah, today I'm focused on the topological property of non-Hermitian bands. If we think about the Hermitian Hamiltonian, we can obtain the real eigenvalue and real eigenenergy bands. And in that case, as I told you in previous slides, the eigen energy band is very simple and trivial topology. But if we think about the eigenstates, we can uh, achieve we can explain the non-trivial topology. But in non-Hermitian Hamiltonian case, of course, the very phase of the eigenstates can make the system non-trivial. But other property comes from only eigenvalue, complex eigenenergy, and exceptional points can make the different kind of topologically non-trivial structures. I'll explain about that using the topological invariant, new kind of topological invariant in non-Hermitian system. Okay, first, I'll explain the gapped phase in non-Hermitian system. This is a Hermitian model. There are two bands. This is a complex energy plane. So these two bands are real. So there is the two real bands, and this is Fermi energy, and this is a kind of reference energy. These two bands are separated by this point. And if we think about the non-Hermitian model, there are two kind of band gap because the non-Hermitian band is complex energy, have complex energy. This is the first band, this is second band. These two bands are clearly separated by this line. So this is called line gap. And always this line gap structure can be transformed into the Hermitian band gap by the proper transformation. So if we think that this Hermitian band is trivial, this line gap is topological trivial because this is the same as the Hermitian band gap phase. However, in non-Hermitian model, this is complex energy. The band can make this kind of circular structures, like the loop structures. And inside this loop, there is reference energy. At this energy, there is no spectrum. So this is also this can be considered another kind of gap. This is called point gap. In this case, this point gap phase bands cannot be transformed to the line gap phase by continuous transformation. So they are topologically different line gap and point gap. So another interesting thing is the Hermitian band gap or line gap case. They require at least two bands for the gap. But in point gap case, if we have only one band, they can make the gap. They can make the point gap. That is interesting points. I'll show the example. This is a very famous example. This is called the Hatano-Nelson model. In this case, 1D chain. If JR equal to JL, in this case, the imaginary part equals 0. So energy is real energy bands and cosine bands. However, if we set the JL is larger than JR, this is the imaginary part, so energy can be complex. In that case, our band structure K equals 0 is this point. This is a complex energy plane. And if we increase the K, they make this kind of circular structure. elliptic structures, and this is 2 pi. So they make the point gap bands in this kind of system. In this, different hopping strengths is called asymmetric hopping or non-reciprocal hopping. In this case, there is the reference energy, and this point gap can be characterized by this spectral winding number. And this is winding number equal to 1. We can make this kind of bands like this, and this is reference energy. In this case, winding number is equal to 2. In this case, winding number equal to 1. In Hermitian band case, there is no point gap. There is just a line spectrum. It means winding number equal to 0. So zero winding number means topologically trivial, and non-zero winding number topologically non-trivial. And in Hermitian case, it's always trivial because there is no point gap. And if we have the point gap, we can define this winding number. And different winding number cannot be transformed each other by continuous transformation. So this spectral winding number is our first topological invariant for our non-Hermitian bands. Okay, the point gap has another interesting properties. If we use the open boundary condition, this is boundary, and this is another boundary. And if we apply to open boundary condition, the point gap spectrum change into the line real eigenspectrum in this model. It means this is called breakdown of conventional bulk boundary correspondence. This is bulk, this is boundary, they have totally different spectrum. So nowadays, currently, there is a new bulk boundary correspondence for this theory, but this is the conventional bulk boundary correspondence in Hermitian case. And another interesting property is this blue spectrum, this open boundary condition spectrum, always localized in one edge. For example, in Hermitian case, if there is the edge states, that is a finite number of edge states, and they localize both of edge. But here, all states are localized. It's totally different from Hermitian edge states. All bulk states are localized at only one edge. In other edge, there is no localization. This is called non-Hermitian skin effect. This state is called non-Hermitian skin modes. Okay, this is a Hermitian case. This is a periodic boundary condition. And this is 2 bands here. And if we think about the open boundary condition, there is 2 bands. If we consider the eigenstates and the bell phase, there is the non-trivial case, there is edge states like this. In this case, there is a standing wave solution here. In this case, many bulk mode are standing wave solution, but there is a finite number of edge states because of a non-triviality from the eigenstates. In non-Hermitian skin effect, we don't think about the eigenstates, just the eigenvalue. There is point gap. If we think about the real energy at this point, there are 2 states. This state has the large imaginary part of the energy. This state is a small imaginary part of energy. This imaginary part represents the lifetime of the states. However, if we think about k, momentum k, this is k equals 0 point. This is positive k. This is negative k. It means positive k component has the long lifetime. So there is a traveling solution. Traveling solution is our eigenstates. If we think about the open boundary condition, this point gap spectrum change into the real spectrum like that. And this traveling solution change into the localized edge states, boundary states. There is no localization here because all states go to this direction. So this is the origin of the non-Hermitian skin effects. And it means the non-Hermitian skin effect require the point gap. If there is no point gap in non-Hermitian case, it's possible. In that case, there is no non-Hermitian skin effect. So this non-Hermitian skin effect is our winding numbers comes from the point gap phase. This non-Hermitian skin effect can be realized in various experimental setup. This is acoustic non-Hermitian acoustic cavity. Every cavity is a cavity. They make the array of the cavity, and between this cavity, they realize the asymmetric hopping or non-reciprocal hopping. And finally, they found all bulk states localized one edge of the array. And this is a non-Hermitian coupled laser array. In that case, they use the open boundary condition. They find the localized skin modes like this. And this is non-Hermitian electric circuit. This is 2D system. They found non-Hermitian skin modes. So except besides this experiment, there are so many experiments to realize non-Hermitian skin effects. So this is a very famous topics in these fields. Okay, in previous part, I talked about our first topological invariant, that is Wien number of the point gap. And next one is I'll discuss the non-separability of the bands. So simply we start from the two-band model, and there is non-Hermitian degeneracy. This is called the exceptional point. I briefly explained the exceptional points. This is a 1D string, and there is the three different standing solutions, standing modes. And if we increase the L, this is closed system, this is bound states, and the energy decrease like this. And we think about two-dimensional system. This is rectangular system. Because of symmetry, this horizontal mode and vertical mode are independent. So this is horizontal mode. It's the same as 1D bound states. And this is vertical mode. This is not depends on the L because this depends on the only H. So they make two modes, make many level crossing because of the symmetry of this rectangular shape. If we break the symmetry, spatial symmetry of the rectangular shape, this is called quarter stadium. In this quarter stadium case, the all kind of spatial symmetry is broken. So all level crossing change into the avoid crossing like this. And if we choose one avoided level crossing, we can make the local effective Hamiltonian for this avoided level crossing. Epsilon 1, epsilon 2 is the uncoupled level, energy level, and C is coupling between them, coupling strength between them. If C equals to 0 case, rectangular case, the C is non-zero case is a stadium case like this. And always we can find the avoided level crossing. The gap size is decided by the C. This is closed system property. This is Hermitian. Importantly, avoid level crossings are very ubiquitous in strongly deformed, desymmetrized to the closed system. This is H0 is our avoid level crossing Hamiltonian, and this is the non-Hermitian part. In that case, we add this level as the change into the resonance. Lifetime is their decay rate is lambda gamma 1. This epsilon 2 has have the decay rates lambda gamma 2, and there is coupling. And if gamma is small, gamma is small or 0, the real part of energy, they show the avoid level crossing like this. And the gap size is smaller. And after critical value, they change into the crossing behavior like this. If we think of the imaginary part of energy, because this is non-Hermitian Hamiltonian, and lambda equals 0, imaginary part equals 0, but lambda is small, they make the level crossing. The level crossing after some critical value, they change into the avoided level crossing like this. We can construct a three-dimensional figure to understand the structures. This is L, this is parameter, this is lambda axis. If lambda is small, the real parts show the avoided level crossing. Lambda is large case, they show the crossing behavior. In imaginary part case is opposite. The lambda is small, they show the level crossing. Lambda is larger, they show the avoid level crossing. And there is clear transition points. That is these points. This is branch points. And at this point, real part are the same. imaginary part are the same. So this is a non-Hermitian degenerate points. We call this exceptional points. And there are branch cut, real branch cut, and imaginary branch cut. But in this line, the imaginary part are different. So this is not degenerate points. So only degenerate point is this points. If we have this kind of non-Hermitian effective Hamiltonian, and we can rewrite this effective Hamiltonian like this using the identity matrix. And this is complex energy, complex value, E1 and E2. And if this effective Hamiltonian has the exceptional point, always this matrix can be transformed to this kind of Jordan normal form by the proper similarity transformation. We cannot use unitary transformation because this is defective matrix when delta equal to 0. So we have to use the similarity transformation. Always we can transform into this kind of form. This form, delta equal to 0 case, this exceptional points, and we use the two system parameters using the real part of delta and imaginary part of delta. So this is a very normal form. And so from this slide, I use this form when I explain the exceptional points. And yeah, okay. The important thing is this avoid level crossing are ubiquitous in strongly deformed 2D closed system. And avoid level crossing should be changed into the exceptional point if we apply the non-hermiticity. It means exceptional points are also ubiquitous in strongly deformed 2D open system, although the name is exceptional. Exceptional point is not exceptional in very well, it's very common in general non-Hermitian system. So we can find easily exceptional point if we have some general non-Hermitian system. Okay, this is a Jordan normal form, and this eigenvalue have the square root branch structure, and this square root branch structure makes this kind of special form. This form is very strange because the two bands or two states, if we start from upper states, upper bands, and we change our parameter adiabatically, very slow, it means we can follow this surface and we can follow this boundary. We encircle this exceptional point by parameter change. At this point, these 2 points has the same parameter set. So after first encircling exceptional point, upper state change into lower states. After second encircling exceptional point, they return their original states. It's not possible in Hermitian case. It's only possible with the exceptional point in non-Hermitian case. And this is clearly permutation operation. It means the first state changes second state changes the first state by one operation. This is permutation operation, and there's cycle of permutation is 2. So we call this is 2 cycle bands or 2 cycle states, and they are non-separable. Imaginary part has same structures. And this is projection figure. I'll use this figure after this slide. This is exceptional point. This is a real branch cut. This is exceptional point. This is imaginary branch cut. This is two system parameter. Sometimes this is a two system parameter. Sometimes they can be kx, ky. It means the momentum space, two-dimensional momentum space. Okay. Yeah, this is the exceptional points for ij state. This is I state, this is j state, and this is branch cut. When we across this branch cut, they exchange. Blue changes red, red changes blue when they across this branch cut. So this is this operational matrix Mij. So our system parameter change along this line. When we across this branch cut, I change into J changes to I. Upper states changes to lower states, lower states changes to upper states. This can be described by this permutation matrix. Sometimes it's called the holonomy matrix. There are many names. And this is I states changed to J states by this permutation matrix. So after first encircling, can be described by this permutation matrix. And this matrix square equal to I, identity matrix. It means after two encircling process, always the states return to their initial states. So this is two-cycle permutation. Another example is this. If we have two exceptional points for three states, we have three I, J, K states. This is exceptional point for I, J states. It means that at this exceptional point, the I state and J state are the same. This is general points. And this exceptional point for J, K states. It means that this exceptional point, J states and K state are the same. It means degeneracy. If our parameter follow this line, and they across this first branch cut, I, J state exchange each other, but K does not affect from this exceptional points. So K maintain their value, their states, and they follow this line and they across the MJK. In that case, J changes to K changes to J. I does not affect. Finally, after first encircling two exceptional points, I state change into the K state change to the J state change to the I. This is M2. Can be described by product of two permutation matrix. And this is the three-cycle permutation. And finally, we can obtain M cubic equal to identity. Yeah, it means these three states are connected to each other in the two-dimensional space. It means this is three cycle states. Can I answer the chat question in chatting?
I think there is still no question in the chat.
Yeah.
Yeah,
Okay.
this is just a
Yeah,
message from
thank you.
the group.
Yeah. Okay, so if we add the exceptional points, we can describe this permutation operation using the product of each permutation matrix. Yeah, it's very simple. This is a linear system, so we can add more and more things. Okay, I just talked about the permutation. Permutation means we have two states here, and this is final states. Can you see my red pen? Okay.
Yes, we
And
can see.
permutation means first state change into second state change into the first state. But if we think about the other configuration, this is upper, but sometimes this can be upper. Oh, sorry. It's not easy. Yeah, I'm sorry. Like this. It means the permutation is just exchange, but if we think about the route to exchange, one is the clockwise rotating exchange, another is the counterclockwise rotating exchange. That is braiding. So our permutation operation can be extended braid operation by the rotating direction. It's not so different. And there are many experimental realization for braid operation in coupled ring resonator with phase and amplitude modulation. In that case, they found they have two states, and when they change their system parameter, they found dislike the many different kind of braiding operation. And this is coupled membrane system. There are three states, and they start from here. This is final state. They change their system parameter. They found a different kind of the braiding operation. For example, in this case, there is three states. After one period, they does not change. But in this case, they start from here. And first periodic operation, they change this state. And this state, second periodic operation, this, and final third periodic operation, they go to the original state. So this is three cycle states. They are connected. They are not separable. Okay, there are many experimental realization of the permutation or braid like this. Okay, in previous slide, I talked about one exceptional point case, and after twice encircling exceptional point, they return to their original states. We call this is one two-cycle states. However, we choose different encircling loop without exceptional point like this. In that case, two bands are separated on this loop. So this is the two one-cycle states. So we use this kind of representation. We use this kind of representation. This is a clear permutation operation for single exceptional point. Our interest is the multiple exceptional point case. In general non-Hermitian system, we can find many exceptional points like this. Every point has very similar topological structure like this. And our question is, if we encircle 4 exceptional points, or if we encircle 8 exceptional points, how different their structures are like this. So we would like to how different kind of structure is possible in this kind of system, depending on the encircling loop. And how can we topologically classify this kind of structure? That is our question. And the one exceptional point can be described the permutation operation. It means the many exceptional point can be described by permutation group. And we can find many permutation related structure. And we can find the conjugate classes of permutation group for these structures. So we can topologically classify these many different kinds of this structure using the conjugate classes of permutation group. Okay, if we have two-state case, there are two different classes, two one-cycle band. This is the same as a Hermitian gapped phase like this. And one two-cycle band is the same as exceptional point structure near the exceptional points. If we have three states or three bands, there are three different kind of classes. One is three one-cycle bands. This is Hermitian bands, like similar to the Hermitian band like this. And this is one-cycle band, one two-cycle band. It means the middle band are independent, but upper and lower band are connected by the exceptional points. And third class is the one three-cycle bands. In that case, if we follow this boundary, they are connected, and they are three-cycle non-separable bands. If we increase our number of bands, we can obtain the more number of possible classes. But this follows the clearly permutation group theory, so we can expect our topological class of the multiband system. Okay, so we consider these conjugate classes. It means the cycle of permutation as the second topological invariant for our non-Hermitian bands. It's totally different of the winding number for the point gap case. Okay, this is example. This is two-band Schuh-Higger model. This is a unit cell. There are two sublattice. There are intra-hopping strength D, inter-hopping strength T exponential zeta, T exponential minus zeta. If zeta equals 0, this is a Hermitian SH model. But zeta does not equal to 0, this is the non-reciprocal hopping. So this hopping make the system non-Hermitian. First, if we think of zeta equal to 0 case, this zeta equal to 0, this line, and T is smaller than T equal to 1 here. This phase is the trivial phase, a gapped phase. I think you can expect the Hermitian SH model. This is a two one-cycle band gapped phase. This black is this phase. This bands and this band are separable by line gap. However, this band has the point gap, the winding number equal to 1 for the point gap, and their second topological invariant two one-cycle bands, 1 to 2. And at exceptional point, and in Hermitian case, this one, sorry, this is a non-Hermitian case. In Hermitian case, this one, if you don't think about the eigenstates, this is also two one-cycle band. these two classes are the same. But if we increase the theta here, this direction, and one Dirac point split into two exceptional points, these two rhythms are same topological classes as the Hermitian case. But this is a new emergent topological phase in non-Hermitian system. And this is this band. In this case, at this exceptional point case, two bands meets, and finally they make the exceptional point here, these points, and they merge. They make the one, two cycle bands like this. And at this point, they split by the exceptional point like this. This is another two one cycle bands. Of course, if you think about the open boundary condition, they have the edge states. They don't have edge states, but in this slide, we don't think about the Bethe phase of the eigenstates. So this and this same class, this are new emergent class. There are two classes for two-band system. If we think about the three-band SH model, and it's the same, we have the same non-reciprocal hopping. And in theta equal to 0, Hermitian case, there are two Dirac points. There are three same classes, three one-cycle bands. The three bands are separable. If we increase the theta, yeah, this part are the same, but and this reason, one two cycle band. This band maintain their shape, but these two bands make the exceptional points and they merge like this. So they make the one two cycle bands. And at this rhythm, two bands are merged. So they make the one three cycle bands. And this rhythm are the same as this rhythm. These two rhythm are same as this rhythm. So we found three different topological classes in three-band model. And every transition occurs at exception point here. Here, this line make the transition. In Hermitian case, or any kind of transition occurs in Dirac point or Hermitian transition points. But in non-Hermitian case, every transition occurs at the exceptional point. So I told about the two topological invariant. So finally, I told about the third topological invariant. It's the same as the Hermitian case. We can obtain the complex Bethe phase using the bi-orthogonality. It's the same as Bethe phase, only different part is this part. This is left eigenstates, this is right eigenstates. Using this bi-orthogonality, we can define the complex Bethe phase, and we can obtain the complex Bethe phase follow when we change our system parameters. So finally, after twice encircling exceptional point, always the states obtain the pi additional phase when we encircle exceptional point. It's well known. So in this case, one two cycle states with pi Bethe phase. This bar represents the additional pi Bethe phase. However, if we think about this loop, this is two one cycle states without phase. We can not obtain the additional phase in this loop. Combining these two properties, I mean the cycle of permutation and Bethe phase, we can reconstruct our permutation group. And we can make the final classification for the using the conjugacy classes of conjugacy classes for our multiple exceptional point case. Okay, so this is a building block for the non-Hermitian topological invariant or non-Hermitian topological classes. This is a schematic figure. This is first band, second band, third band. Different color means different bands. And this is cycle of permutation. And this is a one cycle band. This is two cycle bands. It means these two bands are non-separable. And this is three cycle bands. And this is Bethe phase. If Bethe phase is equal to 0, we represent zero Bethe phase using the normal strip. And Bethe phase pi case is represented by the Möbius strip. We combine this cycle permutation and Bethe phase. This is our building block for our topological classes. This is 1, 2, 3 cycle bands without beta phase. This is 1, 2, 3 cycle bands with pi beta phase. Combining this building block, we can explain our topological property of our non-Hermitian band. For example, in this two-band case, in previous case, I told you this is two one-cycle band, two one-cycle band, one two-cycle bands. They are the same. This red is two one-cycle bands. This blue is one two-cycle bands. If we consider only cycle permutation without beta phase of the states. If we combine two topological invariant, we can classify into the three classes like this, two one-cycle bands. And this part is one two-cycle band with beta phase, pi beta phase. This is two one-cycle bands with pi beta phase. It means this is we have 2 point gap bands with the line gap, and each band has zero beta phase. In this case, each band has pi beta phase. So this is the same as non-trivial phase in Hermitian case. And this is different. This is after twice encircling, they can get the pi beta phase. It's different from, if we think about the edge states, it's different from the Hermitian case. It's not exactly known what the effect of this beta phase, but yeah, we can classify in theory. Okay, if we think of the three-band system like this, in previous case, we have three classes here, like this. That is different color, red, blue, yellow is three different classes when we only consider the cycle permutation. If we add beta phase, we can find 5 different classes like this. And for band system, originally we have 5 classes, 5 conjugates classes, but now we can have the final classification by the 11 classes. Okay, yeah, this is almost final slides. Yeah, this is two-band non-Hermitian SSH model. In this case, we found 3 different rhythms. This is 2 one-cycle bands. This is 1 two-cycle band with beta phase. This is 2 one-cycle band with beta phase. In three-dimensional three-band model, we can find more complicated figure. This is 3 one-cycle band without beta phase. And if they across the exceptional point line, they change the one cycle band here, one two cycle band here with beta phase. Like this. This is different color. And this part, one three cycle bands. And this is one cycle band with beta phase, one two cycle bands. Here, one cycle bands, and two one cycle band with beta phase. This two band has the pi beta phase. And in this case, one on-cycle band and two one-cycle band with beta phase. This configuration are different, but these classes are the same. So finally, we can find all possible 5 classes, 1, 2, 3, 4, 5 in the 3-band model. So let's just summarize my talk. And today I explained about topological invariant in non-Hermitian multibands. First one is the winding number from the point gap bands. And second one is a permutation cycle from the non-separable bands. Third one is bi-orthogonal beta phase from the eigenstates. Sometimes they are independent. Sometimes they are related. So combining these 3 different topological invariants, we can understand topological structure of our non-Hermitian multiband in non-Hermitian system. I think to understand this kind of topological structure of non-Hermitian band is the starting point to understand the more complicated non-Hermitian system. Okay, thank you.
Thank
I'm
you
sorry.
for your very interesting presentation, Professor Jung-Wan. So today talks give us valuable insight about the physics of non-Hermitian system, and also more importantly, the classification of the energy band.
Mhm.
I think there is one question here. Let's see in the chat box. Oh, there are several
sorry.
questions. Let's start.
I'll check the
What is it?
why do we only use the permutation cycle and Berry phase as in the classification?
From Emil.
Can you hear me?
Yes, we
Why
can hear you.
do we only use the permutation cycle and Berry phase as in the classification? Yeah, we use the three topological invariant. First is the winding number of the point gap. We already used. Only things that our system has the one winding number equal to one case. There are many point gap. For example, oh sorry. Oh, I'm sorry. Mm, yeah. Yeah. In this walk, can you see my arrow,
Yes, we
my
can see your
pointer?
arrow.
Yeah, in this case, this wind number is always one for the point gap. If we change our lattice model using the more long range hopping, we can obtain the wind number equal 2 or 3. But here we want to study the simple case, the wind number equal to 1 always. And we add the permutation cycle and Berry phase. It means we use these three different topological invariants for the non-Hermitian band case. However, this is a very simple case, simple situation. If you think about the more complicated situation, we can obtain the another topological invariants. But here, I would like to talk about our basic starting point to understand the non-Hermitian band theory. So,
Is the
sorry.
okay? Thank you. I mean,
Yeah. And
so,
can we realize the non-Hermitian skin effect optomechanical systems? Yeah, of course. I think because you see our first equation is very simple. It's very general equation. I mean, the linear equation, x dot equal to I dx x case. So we can apply this equation to many systems, but only important thing is that we can realize non-reciprocal hopping or not. It's very important. Nowadays, there are many experimental realization in many kind of system. I'm not sure because I'm not expert in optomechanical system, but I guess we can realize, and I think you can find some papers about that. If it's not, you can do that. Okay, I'm not sure the optomechanical system. I don't know exactly. But if we think about mechanical system, we can make the non-reciprocal hopping. And the optical system, we can make the non-reciprocal hopping. There are many experimental realization about the non-reciprocal hopping in various systems. So I think it's possible.
can I ask a
Mm,
question about the non-Hermitian skin effect? So in your example, we only use kind of one dimension.
mhm.
Can we also observe it in higher dimension, like two dimension?
Yeah, non-Hermitian skin effects.
Yes, for
Uh,
higher dimension.
yeah, there are some experiments. For example, here. In this case, this is electric circuit. They make the two-dimensional electric
One
circuit.
dimension.
And one direction they has the non-reciprocal hopping like this. So they found the edge states. In this case, the two-dimensional edge states. So they are point or line. Yeah. So you can make the two-dimensional system using the non-reciprocal hopping. And there is some experimental
Mm.
realization. Mhm.
So it
You can
becomes
find this paper.
like a vertex. How to say it in English? Like the So in 3 dimension, we can also expect this kind of skin effect.
Three-dimensional.
So
Yeah, I think it's
it's
possible, but I didn't see the three-dimensional experiment. Yeah.
yeah,
Yeah,
okay.
I think in principle it's possible, but I'm not sure. Yeah, three-dimensional can be
And
different.
also,
Mhm.
what can we use this non-Hermitian skin effect in application? Can we use it as like sensor or enhancement of something?
Non-Hermitian skin effects. Yeah, in the
Yeah, the
application,
application.
uh,
I
I'm
think
not so sure in non-Hermitian skin effect. There is the many localized states.
yeah. Maybe because we
Uh,
have a kind of accumulations of
yeah,
of
you're right.
eigenstates, we can make
Yeah,
a kind
you're
of
right.
enhancement of something. We can enhance something.
Yeah. Yeah, I'm not sure
Enhance.
in the case. Yeah, if you think about the periodic boundary condition for this kind of system, in
Mhm.
that case, there is point gap in one of the maximum value of the imaginary part of the energy is positive in periodic boundary condition. In that
Mhm.
case, uh, we can find the directional amplification.
Directional
It means the
implication.
because they have the uh, positive value of the maximal imaginary part of the energy, and they make the directional evolution, and they are amplifying
Oh,
for
nice.
so that is the one of the application. But I'm not sure what can we do if we add non-linearity to the system or noise is suppressed. But in linear system, it's very theoretical system, and they increase forever. Yeah, so someone want to use this kind of property for some amplification, but now in skin effect, I'm not sure. Yeah. For
Oh,
example, if we think about the exceptional points, we can use the sensor near the exceptional point because exceptional point has the square root branch structures. It's totally different from the Dirac
the
point and Hermitian
Hermitian.
degenerate points. They have in Hermitian degenerate point they have the linear linear response for the perturbation. But non-Hermitian case at near the
Square
exception
root.
they have a square root case.
Square root
If our
something
perturbation is very small, square root is larger than linear.
large. Yeah.
So we can use the sensor for that. There are many debates because of the noise or the disorder system, but in principle, we can use that for sensor.
Mm.
Mhm.
Okay, let's see the chat box once again. Oh, there are many
Yeah,
questions. Okay,
yeah.
the next question is
Uh,
about non-abelian braiding.
Normal
Oh,
braiding experiment. Could you exceptional point use a realized topological quantum computer? Yeah, everyone want to that. So many researchers want to this. So they study about the braid experiment. Uh, but I don't know direct connection to realize the topological quantum computers. Yeah, but the basic the motivation to study non-abelian braiding, we want to apply this phenomena to the quantum computers and or quantum device. But the but in Hermitian case, they use the ground states. They have degenerate ground states. They are same states, and they make the braiding. But in our case, it's slightly different. Our case is the energy are different, and they make the braiding. So it's not the same as the Hermitian concept. They
oh,
exchange their energy and they exchange their lifetime of energy. So we have to study more for the application. Yeah, I think so. Mhm.
in this in your work, this braiding means we cycle the exceptional point.
Sorry,
We,
recycle?
encircle the
Yeah,
exceptional point, then we
yeah,
create braiding.
yeah, you're right. For example, in that case, the two-dimensional cases, you're right. But if we think about the just one-dimensional case, our SH model is a one-dimensional model. This is two-dimensional experiment. They control the two system parameters. But if we think about this model, this is
Mm.
a one-dimensional SH model. This is a one-dimensional model. There is only one momentum K. In this case, we can reconstruct using the K and system parameter T. This is a two-dimensional case. It means that there is two exception point here, and we can encircle exception point in this rule. However, it means if we use only one K from 0 to 2 pi here, we can make the braiding because this is periodic motion. It's not encircling the exception points. It's just a change of the K. We need just the periodic motion.
Okay.
Mhm.
Let's see another question.
Thank you
This
for
one,
I'd like to ask
the excited one.
experiments of non-Hermitian system. How do we measure real and imaginary energy? It depends on the system. For example, if we think of the optical system, we can obtain the time series and we can make the power spectrum. And the center of the spectrum is a real part of energy. That is frequency. And width of the peak is the imaginary part. And in different system, we can obtain the real imaginary part of energy. Yeah, sometimes they are different. Do non-emission system appear naturally? We always need to construct them artificially. Yeah. For example, in one of my research field is a microcavity. We solve the Helmholtz equation with the outgoing boundary condition. In that case, always the wave decay. It means the wave emission from our cavity, they does not return to the cavity. It means our resonant mode always decay. In that case, non-emission system appears naturally in photonic system. And we can make the artificially. Yeah, that is for example, nowadays the interesting part is the synthetic, using the synthetic dimension, we can make the non-Hermitian system. There are many artificial non-Hermitian system for the engineering. Yeah, both is possible.
And how do we detect exceptional point in experiment?
Experiment.
Yeah, the exceptional point.
Yeah.
How do we detect?
Yeah, it's not easy in experiment. In theory, it's not difficult because we can find the real part are the same, imaginary part are the same. However, in experiment, the spectrum or the energy we can detect easily, but width is not so clear. However, if we have only frequency or energy, I mean only real part, if we found the square root branch structure in real parts,
But then we can expect exceptional point.
yeah, we can expect there is an exceptional point. We can follow the branch cut line, and there is exceptional point. Another way is if we give the symmetry to the system, we can easily make the exceptional point and using the symmetry. In that case, we can make the artificially the system exceptional point for the system.
Thank you. Another question.
Do different topological phase correspond to different macroscopic phase? Topological phase.
Macroscopic. Maybe
Different. Yeah.
Dr. Doni can elaborate the macroscopic phase here.
I'm sorry, what's the macroscopic phase?
Yes. What's macroscopic phase? Can you elaborate more, Dr. Doni? Oh, he's not here.
Yeah, I'm sorry, I'm not expert in the quantum phase transition and macroscopic phase. Yeah. Okay, can I answer this
The next
question
one maybe
later?
first. Yes.
Later. I'm sorry. And in two-mode system, we typically get a single exceptional point. How can we obtain more than one exceptional point? Aha. Do we need to go to higher dimension? For example, if we have the two-mode system, the we can find in very general system we can find so many exceptional points if we can make if we use some special model. For example, our system parameter can be periodic. In the case, the exception can be a periodicity, and this is very special case. Except that for example, this is one example. Yeah, okay, I'll show. In this case, there are two exceptional points. This is two-band model. There are two exceptional points here, and if you change our system, we can make the more exceptional point case. Yeah, so it's not so strange. For example, in one exceptional point and their branch code structure is very local structure near the exceptional points. If we think about the general system, we can obtain the multiple exceptional points. Yeah.
I think there is also so-called
this is one example.
high order exceptional points. So when we have two eigenvalues coalesce, then we have second order exceptional point, and if we have three eigenvalues, then it is third order exceptional point.
Yeah, you're
I'm
right.
not mistaken.
If we have the three states, I mean I, J, K, there are two different kind of exceptional points. One is the second order exceptional point. It means two modas coalesce. And there is a third order exceptional point, I, J, K coalesce together. But in this case, it's very special case. We need more symmetry to make the third order exceptional points. And if we add some small perturbation, this third order exceptional points split into two second order exceptional points. So we can find many second order exceptional points. And if our system has more symmetric, and we can find the high order exceptional point.
Does this order of sorry, sorry. Please continue.
Yeah, but of course there is many accidental high order exceptional point, but in experiment it's not easy to find the high order exceptional point because the second order exceptional point is codimension 2. It means if we control two system parameters, only two system parameters, always we have to find a point. But in the third order exceptional point case, we need 4 or 5 parameters. We have to fine tuning. So usually it's not easy, but if we use the symmetry, we can obtain easily the third or high order exceptional point. There are many methods to make the high order exceptional point.
Does the order of exceptional point affect your classification of the energy band?
In our case, for example, this case, if we change our system parameter, these two exceptional points can meet together and they merge to the third order exceptional point because this exceptional point means I, J state are the same. This exception means J, K state are the same. If we finally control, these exception points are same points. That is a third order exception point. However, we think about the topological structure at this line. Topological structure are the same. The local structure are different, but the global structure are the same. So we don't think about the high order exception point in this classification because we don't need them because it's the same.
They're the same. Okay, thank you. So I think Dr. Doni give us elaboration. Maybe you can check bottom of the chat. So
sorry, I read Nisa's question. Then do we need to go to higher dimension or yeah, okay, if we go to the higher dimension, we can get the more complicated situation, but we only two mode system, we can obtain many exceptional points usually in general system. Yeah, I already answered that. And are there physical system with natural or symmetrical hopping that exists in non-Hermitian skin effect? In many experiments, we use the artificial system. Artificial means we can make the mechanical array. And in that time, we can control the hopping strength in this direction and in this direction. And electric circuit, we can use the non-reciprocal device for the hopping. That is called the INIC, active asymmetric hopping device. And in optical system, it's slightly complicated. In tight binding mode, it's not possible. But if you have the resonance coupling, there is the array like this, and there is another resonator, and we can make the resonator, we can make the hopping via the resonator in this direction, and there is a loss, and there is no resonance in this direction. We can control that. In that case, we can make the non-reciprocal hopping.
Reciprocal coupling.
And easiest way is if you think about the ring resonator, hopping can be controlled by ring waveguide. In the case, we can control the easily. And yeah, so there are many ways to make the natural symmetric hoppings.
Hatano Nelson lattice already realized in the
Oh.
experiment.
Which kind of lattice?
Hatano Nelson?
Hatano Nelson.
Yeah.
Yeah, nowadays during some period it's very hard issues. And nowadays there are many ways to realize this kind of non-reciprocal hopping in experiment. Yeah, that is in resonator system, in the ring resonator system, or in mechanical system, in electric system, there are many realizations about this non-reciprocal hopping. And next is thank you for this. I also want to ask, is there a limit to system environment interaction strengths when system environment interaction? Yeah, I think I'm not sure the question. Always we can make the non-Hermitian description using the trace out our environment, but if this interaction is very small, we can use a perturbation theory from the Hermitian case. But if this environment interaction is very large, we cannot use the perturbation theory from the Hermitian. So in that case, we need a non-Hermitian description, but I'm not sure the exact answer about this question here.
Let's continue.
In some sense, the exceptional point is a kind of limitation because if we increase the non-hermiticity before the exceptional points, the avoid level crossing maintain their properties. Only gap size is smaller. And at this time, we can transform into the Hermitian case. But after exceptional points, they change into the level crossing of the real parts. So in that case, they cannot transform into the Hermitian limits. But I'm not sure this is the exact answer for this question. Yeah, I'm not sure. Yeah.
Maybe. I think in your slide to describe the non-Hermiticity, you how to say add non-Hermitian term to the Hamiltonian.
Yeah.
The non-Hermitian Hamiltonian. But maybe there is also another way to understand the non-Hermiticity by master equation. Will you fill in master equation? So the Hamiltonian stays Hermitian, but then we add the Lindblad terms. Maybe that's
you're right.
That her question, maybe.
Yeah. This question is related to them. So my research is only focused on the Hamiltonian level. Lindbladian in case is slightly different, and I cannot answer about that.
I think there is also so-called Liouvillean exceptional point.
Yeah, so nowadays it's very important and emerging fields for the study of the non-Hermitian physics related to exceptional point and so on. Yeah, it's very interesting fields.
Okay, let's continue to the next question.
Is it correct if I say the second and third topological invariant parameters rise the element to certain breaking group? I say the second and third topological invariant parameterize the element of second means the cycle of permutation, third means the bed phase. But usually we can study about the braid group. we use the cycle permutation, and there is no study. I use the cycle permutation and bed phase, but if you think about the braid group, braid operation and bed phase, it's more complicated, and it's possible, but yeah, it's future work that I I don't I cannot answer about that. Yeah, but it's possible because the in simple system we can do that. In because in braid group is the braid number is very larger, and if we have only two band case, there are so many braid classes, so classification is not easy. Yeah, in some sense, yeah. But, okay. And can you comment on the how can we imagine the classification in more general cases like you demonstrated with the strip and point gap? Should also consider winding number. Mm, More general case means the which kind of more general case? Because I think this is very general. Our classification seems to be very general. I think do you mean the winding number equal 2, winding number equal 3 cases, or in that case it's possible because for example, our cycle of permutation is a kind of fractional winding number. So if winding number can be 1, 2, 3, 4, 5, 6, it's possible. And our cycle is the 1 over 2, 1 over 3, 1 over 4. The 1 over c is the fraction. And of course, the winding number over cycle is very general number. This is not real number, just a representation. And I think that is the general, uh, uh, what's the meaning of with the higher winding? Yeah, higher winding number. For example, in Hatton-Ness model, there is only nearest neighbor hopping. If we add more next nearest hopping, we can make the more higher winding numbers. In that case, we have the higher winding number, and we can combine the cycle permutation and so on. Yeah, it's possible. Yeah, and
This is the
I
the
mean,
quantum phase transition.
yeah,
The last
always
question.
energy gap closing at the phase boundary. I means, yeah, this is sometimes in several years ago, we call this is a quantum phase transition at exception points. But now I'm not sure. Yeah. Quantum phase transition in macroscopic system. We want to call them. Yeah. Okay. I'm sorry, I don't know. Uh, yeah, and two mode system, we typically get a single exception, but how
This is
can we obtain?
you already answered this, so she just say thank you.
Yeah, yeah. Okay. Mhm.
Thank you. So,
Yeah, yeah.
any other
Uh,
question from the audience? So, I have one more question.
mhm,
When I learned about the topology in one dimension Hermitian system, we also have
mhm.
so-called Zach phase. Is it
Yeah,
related
yeah,
to
you're right.
the very phase that you,
Mm.
the very
For
phase
example,
invariant here?
yeah, this is a 1D model. So when we calculate Jack phase, calculate in the 1D direction from k equals 0 to 2 pi. When we
Mhm,
calculate the better phase in this line, that is Jack phase. So this is not quantized in Hermitian system, usually,
mhm,
without any symmetry, but non-Hermitian system, we can consider the loop using this kind of artificial two-dimensional space. This is the kind of encircling loop like this. And this loop, and with this loop, and we can define this loop. This three loop difference, this part, I mean this part are the opposite way, so they can be removed, and this part is common. So if we calculate Jack phase in these three lines, that is same as encircling process in this two-dimensional space. So in the non-Hermitian system, in this the very special Schuster-Higo model, this Jack phase is quantized. Yeah, because the Hermitian limit is quantized, they maintain their quantization of the Jack phase in this model. So this Berry phase means a kind of Jack phase in this case, in one-dimensional
Okay.
model. Yeah, it's very special model. Sometimes it's not quantized. Yeah.
I think in the formula of the Berry phase, we need so-called the eigenstates, right? But
Yeah,
in
from
in
left
non-her
eigenstate.
only left in non-Hermitian.
Yeah, this is Berry phase is this is a right eigenstate, this is a left eigenstate.
Oh,
Only
okay, both
difference thing
of
is this. Yeah, we can obtain the complex Berry phase, and using this Berry phase, we can explain the topological property well. So now we can use this bi-orthogonal Berry phase in
So
non-Hermitian system.
the difference with the Hermitian one is now we have two kind of eigenstates, left and right.
Yeah. This is
Yeah.
in Hermitian case, the left eigenstate are same as the right
Yeah, the
eigenstate.
same right
So
eigenstates.
that is a kind of limit of this value. Yeah.
Okay, I understand.
Mhm.
Is there any more question from the audience?
If we define Berry phase in non-Hermitian system
Okay.
using only right eigenstates, would that make some different compare? Yeah. Yeah, different. Yeah, it cannot explain the phenomena well, because there is some problem of normalization. That is for example, normalization. Yeah, so they can diverge, sometimes diverge, and sometimes they can give the very abnormal values. So we checked many things. Finally, we decided this bi-orthogonal Berry phase is very well in non-Hermitian system.
I think the time is almost up. Is there any last question from audience? Okay, if we don't have any more question, finish this colloquium. So thank you very much for your presentation,
Thank you very
Professor
much.
Jung-Wan, and also thank you very much for the attendance and questions from the participants. So thank you again for sharing your time with us today, Professor Jung-Wan, and we really appreciate your participation as our speaker. Thank you to
Thank you
all
very much
participants. Thank you to all participants for joining us today. We greatly appreciate your participations, and we look forward to seeing you again at our next Brain Quantum Physics Colloquium, and have a great day. Bye-bye.
Yeah, thank you. Goodbye.
Goodbye. Thank you.